In this lesson, we're going to use the limit definition of a derivative to find a pattern that allows us to take derivatives without such a long, complicated process. So bear with me for a moment while I do some of these derivatives quickly so that we can see the result and look for this pattern. So if I want to do the derivative of 5, to find f of x plus h, there is no x plus h to plug into, so we just get the limit as h approaches 0 of 5 minus the original function 5 over h. So this is the limit as h approaches 0 of 0, and we get 0. If we take the derivative of x, then the limit as h goes to 0, f of x plus h would just be x plus h minus the original function all over h. Well, x minus x goes to 0. We have h over h, so we're taking the limit as h goes to 0 of 1, so we get 1. If I do x squared, then we have the limit as h goes to 0 of x squared plus 2xh plus h squared, that's my f of x plus h, minus the original function all over h. Well, x squared minus x squared goes to 0, and we can factor an h out of the numerator, so I get h times 2x plus h over h, and h divided by h goes to 1. We substitute a 0 in for that h that's left, and we get 2x. All right, let's try the derivative of x cubed. If I put an x plus h in here and I multiply it out, I get x cubed plus 3x squared h plus 3x h squared plus h cubed. Then we want to subtract the original function, which is x cubed, all over h. X cubed minus x cubed goes to 0. And we can factor an h out of the numerator. That leaves us with 3x squared plus 3xh plus h squared all over h. And h divided by h goes to 1. When we substitute a 0 in here, both of these terms go to 0, and we are left with 3x squared. So let's look at what we found here. When we took the derivative of 5, we got 0. Well, that would be true for any constant I use. So we can say the derivative of any constant is 0. Whoops, I erased my 1 there. Okay, when we took the derivative of x, we got 1. When we took the derivative of x squared, we got 2x. We took the derivative of x cubed, we got 3x squared. Now I'm starting to see a pattern here. What do you think we would get if we took the derivative of x to the 4th? Well, it would be 4x cubed. There's a pattern here, and it turns out the derivative of x to a power is the power times x to 1 less power. So x cubed, we got the 3 out front, and then we get 2 for a power. X squared, the 2 comes out front, and we get 1 for a power. For 1, this is really an x to the 1. The 1 comes out front, and we get x to the 0. But x to the 0 is just 1, so we don't see it in that answer. Technically, when we're taking the derivative of a constant, we're taking the derivative of a constant times x to the 0. The 0 comes out front, and anything multiplied by 0 gives us 0. So this pattern holds true for all of these. So this leads us to a couple of rules for taking the derivative that means we don't have to use the limit definition anymore. When we take the derivative of x raised to a power, the power comes out front and we get x to 1 less of a power. If we take the derivative of a constant, we get 0. And if we take the derivative of a constant times something, some function f of x, we get the constant times the derivative of the function of x. So let's do some examples. Find the derivative of f of x equals 7. Well, 7 is a constant, and it's the line y equals 7. That's a horizontal line, and horizontal lines have a slope of 0. So this makes sense. Our derivative is slope, and the slope of this horizontal line would be 0. For f of x equals 0, that's the same thing. That's a horizontal line, y equals 0. It's also the x-axis. But the slope of that horizontal line would be 0. Now for this one, I have f of x equals the cube root of x. Now that's actually a power, and I need to rewrite this function so that I can see that power. Well, the cube root is the same thing as x to the 1/3 power. So the derivative of this, a 1/3 comes out front, and we get x to the 1/3 minus 1 would be negative 2/3. For D, we have f of x equals 1 over x squared. Again, I need to see the power if I'm going to take the derivative, so I'm going to rewrite this as x to the negative 2. And then I can take the derivative, a negative 2 comes out front, and I get x to the negative 3. Okay. For E, I have y equals 5 times x to the 6th. And that constant multiple rule tells me to just keep the 5 out front. Then I take the derivative of x to the 6th. Well, a 6 comes out front, and I get x to the 5th. So my answer is 30 x to the 5th. For F, I want to rewrite this so I can see the power. This is 2 times x to the negative 1. So my derivative, the 2 stays out front, and then I take the derivative of x to the negative 1. A negative 1 comes out front, I get x to the negative 2. And so if we clean this up, multiply our coefficients together, I get negative 2x to the negative 2. And it is fine to leave the answer in this form, or you can choose to rewrite it with the exponent being positive. Either way is fine. Okay, y equals 4x squared over 5. Well, this is really just a coefficient of 4/5 that's going to be out front, and then we need to take the derivative of x squared. When we do that, a 2 comes out front, and we get x to the 1. And if we multiply our coefficients together, this is going to be 8/5 x. For h, I want to rewrite this function as y equals 2 times x to the 1/2 power, so I can see the power. So the derivative, the 2 stays out front, and then I'm going to get a 1/2 when I take the derivative of x to the 1/2, and we get x to the negative 1/2. When I multiply my coefficients out, this just leaves me with x to the negative 1/2, and it's fine to leave my answer in that form, or I could rewrite it as 1 over the square root of x. Okay, again, I need to rewrite my original function so that I can see the exponent. So here I have f of x equals 2 times x. Well, this 3 and this 2 mean the exponent's 2/3. And since we're in the denominator, that means it's a negative exponent. So for my derivative, we keep the 2 out front, and then a negative 2/3 comes out, and I get x to the negative 5/3. And if we clean that up, I'll get negative 4/3 x to the negative 5/3. Okay, for J, we have more than one term in our original function. When this happens, we just take the derivative of each term separately. So the derivative of x cubed is 3x squared. The derivative of negative 4x is negative 4. And the derivative of 5 goes to 0. So that's our final answer. Okay, again, we have multiple terms. We're going to take the derivative of each one. So the derivative of my first term, I have a negative 1/2 out front, and then I'm taking the derivative of x squared, so I get a 2 times x to the 1. For the second term, 3 stays out front, and then the derivative of x cubed is 3x squared. And for our last term, the derivative of x is 1, so we just have minus 2. And if we clean this up, multiply our coefficients together, I get negative x plus 9x squared minus 2. Now, we have a fraction here, and I can't power rule this the way it's written. However, when I have a single term in the denominator, I can separate into individual fractions. So this is really 3x squared over x minus x over x plus 1 over x. And if we simplify that, I get 3x minus 1 plus x to the negative 1. I'm rewriting that last term so I can see the power. Then my derivative is just 3. Negative 1 goes to 0, and then we get a negative comes out front for x to the negative 1, and we get x to the negative 2. And I can also rewrite that as 3 minus 1 over x squared. Either answer is fine. And here's another one. Well, now I want to power rule this, but there's multiplication going on here between x squared and everything in the parentheses. So in order for me to apply the power rule, I need to distribute this x squared. And when I do that, I get 2x to the 4th minus 3x cubed. And now it's a simple power rule problem. For the first term, the 2 stays out front. When I take the derivative of x to the 4th, I get 4x cubed. For the second term, the negative 3 stays out front. And when I take the derivative of x cubed, I get 3x squared. And we'll multiply our coefficients together. This gives me 8x cubed minus 9x squared.